Good morning all of you. Thank you for joining me for this video. I am Mr. Ish. This will be just a review video. I have presented several videos with regards to complex numbers. In this video I just want to rehash some of the types of questions I have brought up in those videos as a review of the subject matter. Again, we all know what a complex number is. Complex numbers are basically in the form as I'm going to show you over here. Z is equal to x plus yi. You have a real number component, you have an imaginary number component, and you can of course modify this into the polar or the trigonometric form where you determine the modulus and you determine the argument and you bring in the sine and the cosine functions. You've seen this, and then we've taken this further through a process of the operations where we can do z1 times z2, and we've done z1 divided by z2 where we learn how to multiply two complex numbers and we learn how to divide two complex numbers. Moreover, we also addressed the de Moivre's theorem, and we talked about how we can determine the powers of complex numbers, which look something like this, z to the power of n, and we also determined how we can determine the roots of complex numbers where you're actually determining something which looked like this. We've seen all of this in the previous videos. Here I want to just rehash those types of questions in a review video which should not be too long, and I hope you'll find this interesting review subject matter. For our review, let's use this first question, a basic question. If you're given a question which has a complex plane and you're given a modulus and it happens to be minus 30 degrees, and you're given this, and your question is you have to determine, given the information that you have in front of you, the basic form of this complex number. You know the basic form of the complex number is x plus yi, so we have to determine a form of that. We can start here with the trigonometric form and work actually backwards to determine that. We know what our modulus is, it's 10. We know what our angle is, it's based on your reference horizontal of either 0 or 360 degrees. What's 360 minus 30? It's 330 degrees. And we can determine a clear polar form over here. Our polar form will look something like this. Of this complex number, z is equal to r times cosine of 330 plus I sine of 330. You're going to basically open this up to generate your standard form, which is what we're looking for. You know over here you have a trigonometric ratio involved at 30 degrees. If you're 30 degrees across over here, you know you're dealing with a minus 1 over here in a fourth quadrant. You're dealing with a root 3 as your x value, and you're dealing with a 2 over here. If you open this up, you can even use a calculator if you want. You'll have basically 10 cosine of 330 would be root 3 over 2. Root 3 over 2. And your I sine 330 will be minus 1 over 2 minus I over 2. If you just open this up, you'll actually end up with your answer that you want. 10 times root 3 over 2 is basically saying 5 root 3, and then 10 times minus I over 2 is saying minus 5i. So here we have our basic form, or the standard form of the complex number, x plus yi version, and this is all that we wanted. So here in this question we use a trigonometric form to go backwards to determine the basic form of this complex number. So this is just one example. I'm going to present another similar question just like this next. How about this one? If you're given a complex plane which looks as shown over here on the board at an angle of pi over 3, and you have to convert this complex representation or graphical representation into the standard form. The standard form is of course z is equal to x plus yi. We have to somehow derive this form over here based on what we have. We know we have to work from the polar trigonometric form and work up into this process. We know our argument here, pi over 3, which is 60 degrees. We know our modulus. So we're basically starting with something which can be easily converted into this, and then from this form we can easily go backwards into this basic form. We just have to plug in what we know. We know our modulus here is a 6. We know cosine theta is actually cosine 60 degrees. Pi over 3 is 60 degrees. Let's just keep it in the angle form, 60 degrees. And you know with regards to 60 degrees is of course a trigonometric ratio. 60 degree triangles are 30, 60, 90 degrees. 60 degrees always opposes a root 3. It has an adjacent of 1 and a hypotenuse of 2. So the cosine of 60 is always 1 over 2. And sine of 60 is always root 3 over 2. So when you open this up, you'll basically end up with exactly what you need, which is this. You end up with a 3 plus 3 root 3, and then you can put an I, which is not part of your radical, it's outside the radical, but this right here represents the final answer, the basic form of this complex plane representation, using the trigonometric form and working backwards to determine the regular form. So these are just two basic examples. We'll proceed to some slightly more difficult review examples next, and then we'll of course end this video here with determination of a power of complex number and also with the root of a complex number example. And this video is not going to be a hard video by any means. So in this question, which will be our example number 3, we are given two complex numbers. Z1 is equal to minus 5 and Z2 is equal to 5i. All we have to do is determine Z1, Z2, and we have to do Z1 divided by Z2. We have to do these two questions over here. It makes sense most commonly in these type of questions to start with the complex plane using the plot representation you have. You basically have a minus 5. In terms of a complex number x plus yi, this is really a minus 5 plus 0i, and in terms of this you really have a 0 plus 5i. In terms of coordinates, what you really have is a minus 5 comma 0. In terms of coordinates here, what you really have is a 0 comma 5. If you plot this out, minus 5 comma 0, you end up in this negative x-axis. For this one, 0 comma 5, you end up right here on a 90-degree y-axis. You know the modulus over here. You can do this square plus this square root of, you'll end up with a 5. The argument, of course, is on this is just 180 degrees, which is a pi. Over here, modulus is going to be just a 5. 0 square plus 5 square root, you'll get a 5. And your argument will be pi over 2, which is 90 degrees. We basically have everything we need now to determine the trigonometric or the polar forms. The polar form of this Z1 complex number, of course, is 5 cosine pi plus I sine pi. For this next complex number 2, our trigonometric form is 5 times cosine pi over 2 plus I sine, I was going to put a 5 over here, but I'm supposed to be putting a pi over 2. These type of questions are not hard. You're basically starting with a complex number, you write it in the standard form, you put it into plots, you determine the R and the argument, the modulus and the argument, you convert it into its complex form. And we know the formula for Z1 and Z2 multiplied, or these operations in the product and the division, the quotient. You know Z1 times Z2 is always equal to R1 times R2, and you do cosine theta 1 plus theta 2, and then you do plus I sine theta 1 plus theta 2. These are examples I presented, and the derivation I presented too in my videos. Z1 divided by Z2 is not a difficult formula, it's just R1 over R2, and then you end up minusing these angles. Theta 1 minus theta 2, and you still have a plus over here, plus I sine theta 1 minus theta 2. You just have to plug in what you have into these formulas. If you do Z1 times Z2, and you can always just do Z1 times Z2, you can do minus 5 times 5i, you get minus 25i. That's the most easiest way of multiplying or dividing complex numbers, or you can divide these two. But we are doing it via this process because this process gives us the polar trigonometric forms from which you can do something else. Anyhow, let's go to Z1 times Z2. We get R1 times R2, 5 times 5, which is a 25. So the product of the two complex numbers, you get a 25 times cosine theta 1 plus theta 2, pi plus pi over 2 is a 270 degrees, right? 180 plus 90 is 270, so 3 pi over 2 plus I sine 3 pi over 2. Let's do Z1 divided by Z2. You're going to do the two complex number R values, divide them by each other. 5 divided by 5 is just a 1, and then you end up minusing these angles. 180 minus 90 is a 90 cosine pi over 2 plus I sine pi over 2. If you solve this out, cosine 3 pi over 2 is just a 0, but I sine 3 pi over 2 is a minus I. So 25 times this I gives you a minus 25i. Gives you minus 25i. I'm doing many of these things in my head. You can do them out, open them up, but you'll still get the same results. Cosine of 90 is always a 0, but I sine 90 is an I. So you end up just getting an I over here. So these are our products. The product of the complex numbers is minus 25i, and the quotient of these two complex numbers right here. Complex number 1 and complex number 2 is just an I. Remember, as I was saying, you can do the shortcut. You can just do minus 5 times 5i and eliminate this whole long process, but you'll still get the same result. Minus 5 times 5i, you get a minus 25i. As you can see, I got minus 25i. Then you can do the two complex numbers divided by each other. Minus 5 divided by 5i, you get a minus 1 over I. You can rationalize this I, multiply the numerator and denominator, you get a minus I over I square. You know I square is always a minus 1. You know I square is always a minus 1. Minus I divided by minus 1, you'll just get the 1. I. So look over here, we've gotten the same answers. We've gotten the same answers using the elaborate trigonometric process, the polar process along with the formulas, or by just the simple product and the quotient of these two complex numbers. We've gotten the same exact answers. But I still like this process better because you end up getting trigonometric forms, the polar forms, that you can actually use for other applications. So how about this other similar review type of question? You have two complex numbers, z1, z2. You have to determine the product of these two complex numbers and you have to determine the quotient. Again, you can cheat your way through this and just multiply these across, but I want to do this via the polar trigonometric form. Do not confuse this for being anything tricky in regards to what you might have seen. If supposedly there was a question like 1 plus I to the power of 3 and you have to find this. You have to find this complex number to the power of 3. Here minus 3 is not included in this exponent, so you cannot marry the two items. But oh, look over here, there's no exponent here other than 1. You could literally open up the parentheses and still end up with a usable entity. What I mean by that is, open this up, just write it as minus 3i. Don't feel shy to open this up because there's no exponent here other than 1. And open this up, you get 2 root 3 plus 2i. So now you actually have a clear representation of what you have. You can plot this out. Minus 3 comma minus 3i will put you in the third quadrant. This right here would put you in the first quadrant. You'll be 2 root 3 over here, 2 across. Here you'll be minus 3 across, minus 3, and you have to determine the r. The r over here, of course, is this square plus this square and square root. For square root of 18, you get a 3 root 2. And the angle over here is going to be inverse tan of this divided by this is going to be a minus 45 degrees, which will be minus 45 degrees in the third quadrant will be 225 degrees. Let's just use 225 degrees. I won't write this out as 5 pi over 4, we'll write this as 225. Now let's look over here. This square plus this square and square root, your r value over here will be, this will be a 12 plus 4 is a 16. Square root of 16, you get a modulus of a 4. Your angle over here will be, you can think of it as a trigonometric ratio, root 3 and a 1. It'll be a pi over 6. And if you don't believe that, you can just do this divided by this inverse tan, you'll get 30 degrees pi over 6. Now we have trigonometric processes done and we have to just write this out in the polar trigonometric form. Z1 is going to be 3 root 2 cosine 225 plus I sine 225. Z2 of course will be 4 times cosine 30, let's write it as 30 plus I sine 30. Now for the actual calculation, z1 times z2, you know you have to use the formula r1 times r2. It'll be 3 times 4 times 2 root 2 will be 12 root 2. You're going to add up these angles. Cosine 255 plus I sine 255. Remember, in the product formula you add the two angles. 225 plus 30 is 255. In the quotient formula you minus the angles and you divide the moduluses. 3 root 2 divided by 4, you can just write that as 3 root 2 over 4. You can get a decimal value here if you want, but you'll minus these. 225 minus 30 would be cosine of 195 plus I sine 195. You can solve this out and you can solve this out and you end up having a decimal answer. I don't want to actually solve it all, but you know, you'll open up the parentheses, multiply this with this and add it to this. You'll have a real number and an imaginary number component. You can divide this out, get a decimal answer, multiply with cosine 195, and then you can do the same thing with I sine 195 and you'll have a final answer here, a real component and an imaginary component. So that's this question done for you. I just didn't solve them out. You can solve it out. But I opened it up for you and I brought it to near completion over here. We will look at 2 more examples and that'll be the end of this review. We'll be looking at the powers of complex numbers and we'll be looking at the roots of complex numbers, which are under the de Moivre's theorem aspect of complex numbers. So here's a review question for the de Moivre's theorem. We have to determine, using this, our complex number z is equal to minus root 3 plus I. We have to determine this complex number to the power of 8. And you know, here's a formula for determining the powers of complex number. The complex number to the power of n is equal to your modulus to the same power of n. But then within the parentheses component, your actual trigonometric aspect, the n value becomes a coefficient, n theta and n theta. So cosine n theta plus I sine n theta. We have to determine, using this formula, z to the power of 8. So we cannot proceed right now until we have this written in a trigonometric polar form. So you just have to look over here and plot this out. You have a minus root 3 plus I, which is really same thing as saying minus root 3 comma 1. And that clues you into being in the second quadrant. You're minus root 3 across this way and then you're 1 up. You kind of have a trigonometric ratios here, 1 root 3, 2. You can do this square plus this square and square root them, you'll get a square root of 4, you'll end up with a 2. But that clearly tells you that your modulus is a 2. Your argument over here is going to be based on the inverse tangent of 1 divided by minus root 3. But you know, you have a trigonometric ratio of a 30, 60, 90 triangle. You'll basically end up having over here an angle of pi over 6, which is a 30-degree angle, but in your second quadrant. What's a 30-degree angle in the second quadrant? It's 150 degrees. 150 degrees. But let's bring out the calculator and let's do it. 1 divided by square root of minus 3, and you inverse tan that, I get a minus 30. Minus 30 in the second quadrant is a 150-degree angle. So we have already everything we need to write this in a polar form. Modulus is of 2, cosine, let's write it as 150. I won't put pi over 6, plus I sine 150. Now you just gotta use this formula. We have to determine z to the power of 8. Z to the power of 8 is your modulus to the power of 8. Cosine 150, your n theta, multiply this by your 8, plus I sine 150 n theta times 8. And for this question, let's actually determine an answer, because I'm curious to see what the answer will look like. 2 to the power of 8, 2 exponent 8 is 256. 256. What's 150 times 8? 150 times 8, cosine it, I get a minus 0.5, minus 1 over 2. Let's look over here, there's going to be a positive I. Second quadrant sine angles are always positive. 150 times 8, sine it, I get a root 3 over 2. Root 3 over 2. When you open all of this up, you end up with the following answer. You get a minus 128 plus 128 root 3 I. Minus 128 plus 128 root 3i. So you can just say z to the power of 8 is equal to minus 128 plus 128 root 3, and then we can put the I over there. And it should be a good answer. In our next and last example, we'll be using a complex number to determine its roots. That's also a part of the de Moivre's theorem. We'll be determining the roots of a complex number just as a review. So this right here is our last example for this video. We have to determine the fourth roots of this complex number minus 1 plus 2i. And you know, based on that theorem, here is a formula for determining the roots of a complex number. The root of any complex number is equal to the root of that modulus using the same index. And then you look at the part in the parentheses, cosine of theta plus 2 pi k divided by n plus I sine theta plus 2 pi k over n. The k represents the value of the root that you're looking at, the specific root that you're looking at, always running from 0 up to n minus 1. If you're determining the fourth root, and you have to determine the four roots of this, you're going to go from 0 to n minus 1, which is 0 to 4 minus 1, meaning 0 up to 3. So you'll have 0, 1, 2, and 3, and that'll give you your four roots of this complex number. To start with this type of question, you have to always look at your complex number in the standard form and convert it into the polar form. You see over here, you got something which looks like minus 1 comma 2, which clues you in as being an angle in the second quadrant. You're -1 across, but you're 2 up. And then when you do this right triangle here and you determine your modulus, you know your modulus here is going to be root of a 5. And you gotta determine the angle. You gotta use the inverse tan of the opposite divided by adjacent. So bring out our calculator. Let's do 2 minus inverse tan. I get an angle of -63.4. -63.4 with reference to 180. Just add that to 180. It'll give you 116.6 degrees. 116.6 degrees. Now we have everything we need to write the polar form. This complex number looks something like this. Root 5 cosine 116.6 plus I sine 116.6 degrees. Well, we have to determine this complex number to the fourth roots. We have to determine the fourth roots of this complex number. We have to determine this. If you got 5, if r is equal to root 5, which is the same thing as 5 to the 1 over 2, to determine this part right over here, you're going to have to determine the fourth root of this. So you're going to get 5 to the power of 1 over 8, so you'll get 8th root of 5. That's going to be your modified r, your modified modulus over here. So the fourth root of z is going to be requiring this 8th root of 5. Okay, it's going to be requiring the 8th root of 5. Now let's bring in our k values. We know we're going to have 4 independent roots over here. So when k is a 0, if k value is a 0, right, k value over here is a 0, let's start plugging in the stuff. We have cosine of 116.6 plus 2 pi times 0 over n is 4. My n value over here is what the roots you're determining. Fourth roots means an n of 4. Plus I sine 116.6 plus 2 pi times 0, which is 2 pi k over n, which is a 4. My next one, k value of 1, will be still the same modulus to the 8th root, cosine of 116.6 plus 2 pi times k value here of 1, because here my k value is 1, all divided by 4, plus I sine 116.6 plus 2 pi times k value of 1 divided by 4, and my k value of 2. We basically have 4 of these k values over here, 0, 1, 2 and 3. Let's write it out. Cosine 116.6 plus 2 pi, here k is of a 2, divided by 4, plus I sine 116.6 plus 2 pi times 2 over 4. And my last k value, or my last root corresponding to a k value of 3, is going to be 8th root of 5 times cosine and everything else which comes after it. 116.6 plus 2 pi times 3 over 4, this right here is a 3, plus I sine 116.6 plus 2 pi times 3 over 4. I won't go to the trouble over here of actually solving all of these out, but I will actually go over here and determine what type of angulations we'll be getting. If you look over here, 116.6 was 2 pi times 0 divided by 4, we get 116.6 divided by 4. We're getting an angle of 29.15, which you will run through your trigonometric functions and then multiply it with your modulus, the 8th root of your modulus. What about this 116.6? The next one, 116.6 plus 360 divided by 4, I'm getting here 119.15. Remember, I'm not determining your final answer, I'm just talking about the angles which are involved over here. The angles in terms of how they're increasing for each of the root. Let's look over here. 116.6 plus 720 divided by 4, I'm getting in 209.15. And what about this last angle over here? 116.6 plus 360 times 3 divided by 4, I'm getting a 299.15. So for each of these complex numbers, if you were to graph them out, each of them is basically 90 degrees apart. Each of these is 90 degrees apart. to the next. So you'll end up having a very symmetrical graph. The first complex number will be 29.15 degrees from the horizontal. The next one will be 90 degrees from that. The next one will be 90 degrees from that. And the last one will be 90 degrees from that. But again, I've not solved these out in entirety. I just presented the framework over here which would lead you to your final answer. And the final answer, if you opened everything up over here, would be all decimals. You'll clearly end up with decimals. And you can see everything here is in terms of the angulation, 29.15, 119.15, and so on. Each angle or each complex number root is always 90 degrees from the next complex number root. So that's this example pretty much done. You can finish it out on your own. So with this review video now coming to an end, you can see all the types of questions I went over. Pretty much you've seen those questions in the previous videos about the complex numbers. I hope you enjoyed this video. I tried to keep it short and sweet, to the point that is. Please like, subscribe and share. Thank you for watching this video. Have a nice day. Bye.